Hello everyone, welcome once again to another seminar of IAG Astronomy Department. Thanks for joining us here or through our YouTube channel. And today's speaker is Ana Queiroz. Many thanks, Ana, for being here today, for accepting our invitation. And Ana got her bachelor and master's degree in physics from Universidade Federal do Rio Grande do Sul. And currently she's an advanced PhD student at AIP Potsdam. And her talk today is about unveiling the inner galaxy stellar populations and their relation with local samples. And let me ask you, everyone, please turn off your microphones and cameras during the talk. And if you have a question, you can raise the digital hand here in the Google Meet, or you can write it down in the YouTube chat. The questions will be asked after the presentation. So Anna, whenever you are ready, you can start sharing your screen.
Okay. So I hope you see my screen.
Yes.
And I will turn on the laser point here. First of all, thank you very much for the invitation. I'm very happy to speak here at IAG. And thank you for the introduction also, Maria. So I'm today speaking about the inner populations in the center of our galaxy and what is their relation with local samples. And this is the central topic of my thesis as well. And this wouldn't be possible without the data from the APOGEE survey, which is a survey from the Slow and Digital Sky survey, and also from Gaia. And my advisors here at AIP are Christina and Matthias Steinmans. So to introduce the theme, I am going to talk about the inner parts of the Milky Way, which is our galaxy. And studying the inner part of our galaxy compared to external galaxies has the advantage that we can have a lot of detailed information about the individual stars. But this advantage comes with a lot of challenges, mostly because as we are inside our own galaxy, it's difficult to have a very good picture of the structure. And also because between us and the inner galaxy, there is a lot of dust, which obscure the stars and it's very difficult to observe. Because of these difficulties, actually, the detection of the bar component of our galaxy was only confirmed in the early 90s. So it was only in the 90s that we really confirmed that our galaxy is not only a spiral, but a barred spiral, which is characterized by this cylindrical or square shape in the center. This was done with confirmed finally with the COPE project and DERB. And in contrast, nowadays we have the Gaia, and the Gaia satellite here is measuring parallaxes and proper motions for more than 1 billion stars. And with the parallaxes, we can access the distance. And here, with the help of Starhorse, we access the distance in Anders et al. 2019 for around 300 million stars using photometry and Gaia. And here we see the classical illustration of what in the foreground of what we expect our galaxy to be. And in purple is this structure recovered using the distances from Starhorse. And you can finally start to have with real data this picture as if we are looking our galaxy from above. We'll talk a bit more further on about the method Starhorse. But of course, since the 19th, it was not only Gaia that came. A lot of photometric and spectroscopic surveys were done dedicated in the inner galaxy. They mostly operate in the near infrared so that we can peer into the dust. And here, for example, it's shown from the review of Barbui et al. 2018 about the galaxy bulge. We see the distribution of the spectroscopic surveys that were dedicated to this area. And we see we cover a large area, but it was difficult to cover the very low galactic plane, like with latitudes below 5 degrees. But all the surveys and also the photometric surveys help us with a lot of information. So we know that in the inner galaxy, there is a triaxial bulge X shape. So this is part of the bar, and it's also called boxy peanut shape, which is the structure that we see from edge on, from where we are in the center. And we also know from the measurement of velocities that the stars follow what is called cylindrical velocity, which is this dependence of the galactocentric velocity with the galactic longitude that forms this sort of S, which has also been detected in edge-on external galaxies that are barred. Also, we know, for example, with the VVV, which is a very large photometric survey in the inner galaxy, here we see this peanut boxy shape in the center. But besides that, there is also a long flat bar that extends to higher longitudes. Besides this barred component, which has been measured mostly to be metal rich, there is also a significant detection of stars that are metal poor and do not present any rotation at the center. We also know a bit about the ages of the stars, so it's very hard to have individual ages for the stars in the inner galaxy. But for example, with color magnitude diagrams, we know that most of the stars in the inner galaxy are older than 8 gigayears. But there is also some stars that have been detected through microlens technique, for example, that present a very younger age. And another interesting feature of the center is the metallicity distribution function, that it's multi-peaked. So on this last work from Rojas Zerragada in 2020, he shows the metallicity distribution of the stars for different pings in latitude. And we see, for example, for lower latitudes, we have a peak. So we have mostly 3 peaks always, but the prominence of the peaks changes with the height from the galactic plane. So for lower latitudes, we have a more prominent metal-rich peak. And when we walk to higher latitudes, we have a more metal-poor prominence of stars. So I talked in the beginning that one of the challenges of the inner galaxy is then the extinction. But after we overcome this, there is also now the problem that we are facing, which is this coexistence of several populations. So we see there is this metal poor that has no rotation. There is also the long flat bar, also this boxy peanut component. And besides that, there is also the contribution of the other components of our galaxy. So there is the contribution also of stars from the fin and the thick disks and the halo. So it becomes very problematic because all this population also overlap in chemistry and kinematics. So how to really efficiently understand what is the contribution for each component there. And that's more or less what I want to try to answer. And for that, I will use the data from Gaia, so the parallax and the proper motions. I will join then with the APOGEE survey. So APOGEE is very special because it's a high-resolution spectroscopic survey in the near-infrared. And in its latest release, it's going for more than 600,000 stars and covering very well even low latitudes, like lower than 5 degrees. And it's measuring more than 20 abundances for the stars, the atmospherical parameters, and also the line-of-sight velocities. So it's a very complete survey. And combining this with the parallaxes, we have also access to the full phase space, so the positions and the 3D velocity. We can calculate then the orbits of the stars. So, but the parallax itself, if you invert, you can have access to a distance But for the inner galaxy, that is problematic because the uncertainty of the parallax is very high. So we are talking about distances of more or less 8 kiloparsecs. And so to have uncertainties of distance that are reasonable for the inner galaxy, we need to use also the other information that we have of the stars. So we combine the spectra, so the temperature of the star, the surface gravity, and the metallicity with the photometry, like infrared photometry and also optical photometry, and combine this with the parallax into a Bayesian tool, which is called Starhorse, which takes into account also the priors for the galaxy, because we know, for example, that the density of stars is not the same everywhere we look. So we take this into consideration also in Starhorse, and we can then derive distances and extinctions for the whole apogee. Here, apogee DR16, which has around 400,000 stars. And in Queiroz et al. 2020, we do this for other spectroscopic surveys as well, like RAVE and Gaia. And here, of course, I will focus on apogee because it covers the low galactic plane where I want to study. And one of the main results of this paper that's very interesting and was also highlighted in the collaboration meeting of this longitudinal sky survey is that we could, with this distance, extend the maps of alpha over iron against iron over H for the very inner radii and the very outer radii also. So here it's shown this the diagram of alpha over iron for different beams in R. So as you walk to the left is the inner galaxy, and as you walk to the right is the outer galaxy. And the higher beams are the most higher beams from the galactic plane. And before we had from apogee DR14 in Hayden, we went only until R 3 kiloparsecs. And we finally, apogee DR16 with Queiroz, 2020, we can finally go to the most inner beams with statistics of thousands of stars. And one of the most important results here is the clear bimodality, so the chemical duality of the alpha elements and the metallicity in the center. And that is very much detached for this very central beam here, where it ranges from R0 to 2 and from the most inner galactic center, 1 kiloparsec of height. So, but we are here not interested in the whole disk, but in a sample that ranges in the most inner kiloparsecs of the galaxy. And to do that, we will select two samples. The first one, it's called Beautybar sample, and it's a simple with square defined in Cartesian galactocentric coordinates. They are plotted here, so X and Y, and also Z and R. And we select this region inspired by what we see with Gaia and photometry and Starhorse that I showed before, where we see the clear overdensity of the bar. And we select then this region. But of course, here we don't have the spectra, so the distances are less precise, but you have much more stars. So we can be inspired by this region and do the same for apogee now, which has spectra, and then therefore we have preciser distances. So this studied box has around 26,000 stars. And as we can see also here in the distribution, even though apogee is covering the very low galactic plane, it still lacks some line of sight, for example, here below 200 parsecs. And as you can see, the extinction is very high for this region. And if you're interested in Starhorse results, be aware that soon we will have also a new paper with Gaia EDR3 and photometry. So the first sample, it's this one defined with the ranges of X, Y, and Z. And inside the sample, we want to do a better cleaning because definitely inside this range of 5 kiloparsecs, we have also stars from the disk. And to clean for these foreground stars or disk stars, we use this technique which is called reduced proper motion diagram. And it is analogous to a distance modules, as you see here. But instead of the distance, you use the proper motions. And this will highlight then different populations when we do the diagram against the color. And here you see that for our whole Beautybar sample, we have mostly 2 overdensities. The one that is more constant with the center when we cut in the LB is the one that is highlighted by the red square. So for simplicity, our more clean sample called reduced proper motion sample is everything that falls in this red square. And we can see that it results in a more central distribution of the stars. You can also see that the distribution for the distance for the 2 samples, the reduced proper motion sample is much more centered at 8 kiloparsecs, which is more or less the distance of to us from the center. And the Beautybar sample has a considerable amount of stars at 4 kiloparsecs, which is then cutted, but without an abrupt cut in distance with the reduced proper motion sample. So it works like a filter for disk stars. Now we will study the different distributions for these 2 samples. So here we start with the distribution of the alpha over iron for the Beautybar sample and reduced proper motion sample, or RPM. And we see that there is this, again, the clear chemical duality. And as when we do clean for the RPM, this detachment from the 2 sequences even more evident. We can also see, for example, if we plot again the distribution of X and Y and color code this by the metallicity, that the stars with they are more metal poor, they are distributed in a different way. So they seem to be more concentrated in the center. But when you see in the maps of Z against R, you see that these are not they are not confined to the low height. And in the very low height, actually, what dominates is the more metal-rich stars. Even though we lack again especially these 2 line of sights here. So this has also been studied before, that the distribution in the center of the stars that are more metal poor, they are in a more spherical distribution, and the metal-rich stars are more concentrated in a square distribution, which is more constant than with this boxy peanut shape. So now we can also use the kinematics because we have the line of sight velocities and the proper motions. So we can calculate the 3D galactocentric velocities. So here I showed the galactocentric VR velocity for the stars. So this is the color code in the projection of X and Y again. And here we can see what is called this butterfly effect, which is this clear quadrupole, and it's characteristic of the axisymmetric potential of the bar. And this is also very interesting to compare with simulations where one can then characterize better the extension of the bar and also the angle with the GC line. And here in the middle panels and the rightmost panel, I showed then the distribution of the rotational velocity or azimuthal velocity against the galactocentric radii. We can see that for the bar Beauty sample, we have a huge overdensity of stars at 200 kilometers per second. It is what we expect for disk stars. When we clean for the reduced proper motion sample, we have that most of the stars vanishes. So which it means that our selection is also working as we want. And in here is interesting to see that the overdensities look that there is a population more confined to the inner radii, but it has a very large dispersion in azimuthal velocity. And another density that grows, that the velocity grows linearly with the radii. So this seems to be, again, constant with a bar rotation, so with a rigid body rotation, right? So now here I show the same maps. So the rotational velocity again against the galactocentric radii, but now color-coded by the metallicity and the alpha elements. And we see that most of the stars that are in this rigid body rotation are metal-rich, and there is the concentration of stars here. There is metal-poor and has a large velocity dispersion. So as I told, this has been seen before, also recently, for example, in Arensen 2020, where she studies very metal-poor stars, and they also show this clear velocity, higher velocity dispersion. Now, this was all the present position of the stars. To fully characterize these populations, we need also to calculate the orbits. And for this, we had the help from Ángeles Pérez-Villegas, and we calculate then the Milky Way. We calculate the orbits using a Milky Way-like potential with Miyamoto-Nagai disks, Navarro-Frank White dark matter halo, and the triaxial Ferris bar, which is explained on the paper from Pérez-Villegas and Porterio. And using Monte Carlo analysis, we can then have the median parameters of the orbit, and we then use to this diagram here to show the Zmax, which is the maximum height of the orbit in relation to the galactic plane, and the eccentricity of the orbit. So low eccentricity orbit is almost a circular orbit, and here it's a very eccentric orbit. And we do this only for our cleaned sample, so only for the RPM sample, which has around 8,000 stars. And we see that most of our stars will have a very eccentric orbit and are at low Zmax. We also see, again, and when we color code the same map by iron over H, that there is a clear gradient with the metallicity. So as we go to higher Zmax, we have more metal-poor stars, which has also been seen before, as I said, like from Rojas Regada, which shows that the metallicity gets more prominent metal-poor in high latitudes. And this is also shown here clearly in the orbits. So now I will use a technique that was firstly done in Boesche 2013 to study disk stars kinematics, which is to divide this plane, the Zmax against eccentricity, in these 9 ranges that are labeled by the letters. In each one of these ranges, I will try to understand some distributions for the stars. So here I will start with the metallicity distribution. So don't forget, the higher panels are showing high Zmax orbits, and the rightmost panels are showing high eccentricity orbits. And for our most populous bin, high eccentricity and low Zmax, we have a very broad distribution in the metallicity, but a very prominent peak at high metallicity stars. When we walk to low eccentricity, this narrows down, and the peak at high metallicity gets less metal rich. So here around 0.2, here goes at around 0.25 at least. This is interesting to capture here, this very high metallicity stars also in the center, since there is, for example, the problem with radial migration. So we see stars also in the solar neighborhood that have that are very high in metallicity and that probably could not have been born there. This has been recently in the papers from Milio 2021, also in Trevisan 2011. And also from these distributions here, we see again this the clear gradient with Zmax and metallicity. But it's interesting to notice here that the metapoor stars, they are still there at low Zmax, but it's the metal-rich stars that vanishes. So the R contribution for metapoor stars seems to be at all pins in Zmax. Now, another interesting parameter to see in this space is the rotational velocity, so the V phi. And we see again for our most populous bin, we have a broad distribution of V phi, but it gets even broader when you go to higher Zmax, which is also expected that you have more dispersion and more hot population for high Zmax and high eccentricity. But the interesting thing to see here is that at the window of high eccentricity and high Zmax, there is a very extended tail to negative velocity or counter-rotating stars. And this tail has also been detected in Lucey et al. 2021, studying also the COMBS survey, so very metapoor stars, where there is also this tail of counter-rotating stars that do not match the simulations of the APOGEE area. And as we go to low eccentricity, we have this very narrow distribution at more or less 200 kilometers per second. Again, this bin seems to be very consistent with inner thin disk stars. So, but now, where is the contribution of the bar in the orbital space? So here I will show again the 9 ranges, and I will show the distribution of the alpha over iron against iron for each one of the windows. But I will color code this every point as a probability to be in a bar-shaped orbit. So the bar-shaped orbit, it's calculated using frequency analysis on the referential of the bar. And so all stars that have this frequency will be in what's called a bar-shaped orbit, which is characterizing this boxy peanut structure. And using, again, Monte Carlo analysis, we can assign a probability to it. And here we color code this by this probability. So we see that most of the stars that have high probability to be in bar-shaped orbit are at the high eccentricity and low Zmax. Again, what you expect for a bar. But what is very interesting here is that the bar stars, they are not confined to be only in one sequence. They are not only alpha rich or alpha poor. Here you cannot even distinguish if there is more alpha rich or alpha poor stars. But if you count them, so all stars that are with probability higher than 80% on this window, for example, you see that there is more stars that are alpha poor, but there is a very considerable stars in bar-shaped orbit that are alpha rich. So this suggests that the evolution of the bar has a strong efficiency to trap stars from the disk or from this spheroidal metal-poor component that is in the center. And that is trapped by the potential of the bar, and also the stars fall in bar orbits. Now we go to the second part, where we'll try to compare what is the contribution of the local samples in the inner galaxy. So for that, I will use the same, so this is new, and this is now with APOGEE EDR17. We will select the same bar-Bode sample with the same ranges in X, Y, and Z, but on APOGEE EDR17. So now we have 30,000 stars, and we will select a sample that is contained to the solar neighborhood around 1 kiloparsec from us, which is showed here as this distribution, so around 30,000, 13,000 stars. And now, to understand the populations in the local volume and in the inner galaxy, I will use the technique which is called T-distributed stochastic neighbor embedding, so TSNEA. The TSNEA is a technique to deal with the multiplicity of the dimensions. So you give a set of information, so a set of dimensions to the TSNEA technique, and it will project all this information in a 2D frame, as is shown here, TSNEA-X and TSNEA-X and TSNEA-Y. But this projection will contain the previous information that it was given by getting the similarities between the points and projecting them to very closer points. So it will calculate a sort of distance which compares to the similarities of the information that was given to the TSNEA. So I'm not the first one to use TSNEA in astronomy. It has been used also to validate pipelines, also to find chemical similarities, as here in Anders et al. 2018. So I will use this technique in the local volume, and I will use only chemistry as information for the TSNEA. So these are all abundances that are given by APOGEE, and these abundances are also available for a considerable amount of stars in the inner galaxy. But here, the local volume first, we, running the TSNEA, we find mostly these three groups. When we project to the Y and X TSNEA, they are color-coded by the different colors. When we project this into an alpha element and the iron, we see that they distribute mostly of what is known as the genuine thick disk. Transition stars that are in between the thick disk and the thin disk. So transition stars or bridge stars, they have also been detected in the works for Chuka et al. 2021, where they studying also the ages of the stars. They seem to have a different origin as the thick disk and the thin disk. When we see, so here I showed the cumulative distribution for the same groups that were found in here as age. So the age from Starhorse is not, it's still as isochronal fitting method, so it's not very precise. And we have also the eccentricity here and the Zmax. So we see that thin disk stars have a much younger age than the transition and the thick disk stars. And we see again for the eccentricity, so we have lower eccentricity stars, and it starts to get more eccentric as you go to the thick disk, genuine thick disk. And again, the Zmax is also much higher for the thick disk. Now, I want to compare what I found in the local volume with the inner galaxy. So here, forget about the transition stars. I just showed the genuine thick disk and the thin disk found in the local volume with the TSNEA in oxygen and iron. And I will use these contours and plot them above what we have of the distribution of oxygen and iron for the inner galaxy. And I will show for different ranges of eccentricity and Zmax, the same windows as we saw before, but special ones for cell C, for high eccentricity rings and high Zmax. We see that there is some contribution of what we detect as a genuine thick disk, but it's not exactly. So there is something else that it's more metal poor and that extends more to this metal poor side. There is almost no contribution of thin disk stars at this range of eccentricity and Zmax. When we go to the range of low eccentricity and low Zmax, so we have a lot of contribution of inner, what we think it's inner thin disk stars. So it doesn't match entirely what we see in the local volume because there is this non-gradient of the metallicity with the radius for the inner thin disk stars. So as much as you go to the inner galaxy, you get more rich in metals for the thin disk. There seems to have some contribution of thick disk stars, but it's not a lot in this range. When we go to cell I, so with eccentricity around very high and low Zmax, we seems to have both contributions, but again, it doesn't really match very much what we see as genuine thick disk, and again, much more metal rich than the local volume thin disk. At cell E, which has intermediate eccentricity and intermediate Zmax, we have a much more contribution of thick disk stars. So this has seen before also chemical similarities between the bulge area and the thick disk. But now to understand better what is the contribution of thick disk stars, we will do again the TSNA, but for the sample of the inner galaxy with the same abundances group that we used before. And in the inner galaxy, it finds at least these 4 groups that separate in these islands. And when we project again into the alpha over iron, we see that the group color-coded by black here is really similar to what we expect for the genuine thick disk. So apparently here we can detect much better with the TSNA what is the contribution of the thick disk stars. We see again the green stars, which it's mostly tracing the inner thin disk stars. And we have this also the cyan, magenta, and orange populations that are in weird locations of the alpha over iron. But they also overlap with the thick disk, as you see here. So here is the next question: where and what would be this magenta and cyan stars? So again, investigating then the eccentricity and the Zmax, we see that the cyan and magenta stars, they are much more eccentric. They're also not confined to low Zmax. Again, this is the cumulative distribution. And here we can see the distribution of the rotational velocity. And it's interesting that here we see that the magenta and the cyan are tracing a bimodal distribution in the rotational velocity. And that seems to trace this extended tail that was going to negative velocities. So it could very possibly be that this are debris. So it has been several new papers that have been detecting debris in the bulge area as well, like Trincado 2021 with high nitrogen stars, also the population found by Orta, and this counter-rotating again in Doucet 2021. So what is next to be here is definitely to understand better and compare with the debris that were already found if it is exactly what is being tracing by the magenta and cyan population. And the orange one is also different and needs to be investigated. So I think I can stay here. So my main conclusions are that in the inner galaxy, we see this clear bimodality in high alpha and low alpha stars. They can be tracing then totally different formation paths. This is also seen by these models from Capini, for example, with the true info model, where you have this gap between alphas. And we see that in the kinematical plots and also chemical plots that the bar is complex chemically, so it's not made of only one sequence. And this suggests, again, this efficient trapping of the stars by the potential of the bar. It has been also seen in our earlier studies that stars that are metal poor were also following bar orbits. And we see with the TSNA that the thickness does not change with radius. It is the same in the local volume and in the inner galaxy. And with the Tessinae, we seem to be able to separate this population. So counter-rotating and debris, what are they and what are these extra populations that we found? We still need to investigate better, but there are several options. As I said, different debris that have been found in the inner galaxy. As well, there is this splash population, which was so from the protodisk and was perturbed by mergers. And I guess that's it. And thank you very much. Here's a picture of the Starhorse team and one of the times we could meet during the pandemic. And also Basilio is part of it. And any questions, please can make now or can contact me later as well. So thank you.
Thank you. Thank you so much, Anna, for your talk. And so let's start with the questions. There's one hand here. And one question. Maybe, Reinaldo, would you like to start?
Yes, thanks, Maria. Thanks, Anna, for the talk. It's a question from Bruno Diaz. He works in ESO, if I'm not wrong. And he put his question in the YouTube channel. So I'll read it. He first compliments you, great talk. And he says, many globular clusters have different kinematics and metallicity with respect to their nearby field stars. APOGEE has observed many globular clusters in these fields. So his question is in two parts. Do you have to clean up your sample also from globular clusters? And how easy can you identify globular clusters in your maps?
So thanks, Bruno, for the question. Yes, so wait. Yes, I think, so I haven't really cleaned, I cleaned for the flags before, but I haven't really done a selection on clusters. So there, we also have a prior now for the most clusters, for globular clusters and open clusters and Starhorse. So we can take the ones that we mostly see in the overdensities, but yeah, this probably should be taken into account better also. Don't know if that answers so well the question, but there hasn't been a very special cleaning for globular clusters besides the positions.
Great. So for the moment, it's not possible to identify the globular clusters. Is it so?
The ones that are known, yes, but the ones that maybe still are to be discovered, not, of course.
Right. Thank you. Bruno, if you want to complete the question, please, you can continue in the chat. I will bring it later. Thank you, Anna.
Thank you.
So, Vechi, you can ask your question, please.
Oh, hi, Anna. Thanks for the talk, very interesting one. And I'd like to make to you a very similar question to the one that I made to Cristina Chiappini when she presented this overview last week in the SAB meeting, if I may. And the question regards the extension of the bar. Since these distributions of stars do provide some signature of the bar itself, can you predict, based on these signatures, the extension of the bar of our galaxy, or other words, or else can you combine these observations with, for instance, observations of clumps or star-forming regions, massive star-forming regions in the galactic center that also provide some signature, as the recent paper by Shaila Atker and collaborators. Can you combine these different observational signatures in order to get an extension or a reliable consideration over the extension of the bar?
Thank you for the question. So first, I don't know if it was clear. So with the Starhorse method, we derive extinctions and distances. So this works as with the Bayesian method, where we compare everything that we have. So the spectra from the star with the photometry and the parallaxes from Gaia. And we also use a prior estimation of the extinction. For example, on APOGEE, we use as prior what they use as targeting, as the extinction for the targeting selection. And then the Starhorse will have a range of extinctions around this prior and determine together with the distance this both parameters. So there are a few biases. One of the most important here, maybe that cause a bias, is the high variability of the extinction law in the inner galaxy. Has been reported by VVV also that it varies. This is a bit complicated to put in the code yet, so this is one of the biases that it might have. But the extinction, yes, it has to be determined with the distance so that we have also a good distance. And for example, in unders, where there is no spectra, and that was calculated distances and extinctions for Gaia and photometry, we had a limitation before that the AV would go only until 4. And this actually, I think, pushed a bit the angle of the bar, since it's then here crucial that we have a good extinction determination to determine the distance. Maybe this can be improved later, as you said, with other measurements, and also maybe trying to improve this extinction law in the inner galaxy.
Okay, thank you.
Okay, Reinaldo, you can ask your question.
I think in the first part of your talk, you told us about a technique, if I'm not wrong, reduce the proper motion.
Yes.
Some technique. Could you explain a little bit more? For me, it's something very new, and I could not understand why does it work, this technique.
It's here. So yeah, it's the proper motion is a proxy for the distance, because more distant the star is, it moves less, and so this is analogous to the distance models, and it will more or less detect the stars that are at different locations, and combined also with the color, right? So it's very analogous to distance models, but it has how can I say? So Starhorse calculating the distance, it has we take in account the priors, we take in account again this, for example, the extinction law. So we wanted here to do a more let's say primitive cut just to filter the stars. And that's more or less what we achieve with this, using the proper motions. And I think here what we wanted is also to be able to use all the different measurements. So first we have the distance that are based on the parallax, photometry, and the spectra. And here you have a proxy for the distance, but with a different measure, which is the proper motions. And the proper motions on Gaia EDR3 are very precise, also like 2 times more than Gaia EDR2. So that was more or less our what we wanted here. Is it clear? It's more clear, or?
Yes, thank you. Now it's more clear. Yeah. Now I see it's related to parallax. Then.
It's related, yeah, exactly to the distance.
Reinaldo, if you see in the YouTube, there was a second question from Bruno that is in the chat also. Okay, but okay.
Okay.
Okay, I just have a question. You mentioned that there was these high metal stars that they suffer some radial migration. What is producing this migration?
So the radial migration has it's more what is detected in the disk. So by works from Minchev, for example, and Christina, where you detect in the solar neighborhood stars that are very rich in metal. So they are much more rich in metal than the ones that are mostly detected in the solar neighborhood. And if you put this into when you have ways to measure the age, for example, or the birth radii, you see that the stars that are this metal-rich stars, they are also have intermediate, so they are a bit older than in the solar neighborhood, and this it's coming mostly from the center, because we see here that in the center there is a high quantity of very metal-rich stars. And they suffer radial migration mostly because of interactions with the bar and the spiral arms, if I understand well. And this is mostly happened for the stars that have rotation already, so it's more efficient for the thin disk stars.
So that's why this, as it's more efficient for this kind of stars, that is why they migrate, because this doesn't seem to be related to the fact that they are high metals. It's because of their rotation.
It's because of their rotation, and it has nothing. It's not related to the high metallicity of the star, but because the high metallicity stars, they are mostly in the thin disk, and they have rotation. Exactly.
Okay. Okay, thank you. Reinaldo?
Yeah, there is a question by Andrea Miloni. He first compliments you. Excellent seminar. So his question is, are the 2 alpha iron stellar sequences at the Beautybar actually connected to the 2 info episodes? If so, what about the intermediate alpha iron sequence?
Very good question. I don't know if I know how to answer this so well, but so yes, I believe they probably are related to the 2 info model. The intermediate, what do you mean intermediate sequence? This one that was detected here. Yeah, I don't know how to answer exactly in the matter of deformation, but yeah, this could also be from the radial migration of the stars, and so, but they have, it has been detected that they have a bit of a different age from the thin disk stars. I'm sorry, I don't know how to answer this so well.
So he also asks, could it be made by an early gas-rich minor merger or a gas radial migration driven by the bar instability?
Yes, I guess it could. That's very interesting to understand better also this transition stars. And the fact that in the inner galaxy, I didn't find them so easily with the TSNA. So maybe they are more mixtured with the thin disk here and the inner galaxy than they are and the local volume. But this, I'm not sure of where I'm talking still here because this is new. But yeah, this definitely is very interesting.
Thank you, Anna. Thank you, Andrea, Meloni, for the question.
Okay, so if there is no more questions, thanks again, Anna. Thank you very much for your excellent talk. And many thanks everyone joining us, especially through YouTube and here. So
thank you very much.
Thank you. Thank you.
So we can finish the broadcast,
Yes,
Richard.